Welcome back. In the last couple of videos, we've been talking a lot about potential. But of course, when you have potential, you ask yourself, well, what can you do with it? And we're going to start talking about circuit elements and how we can find some interesting physics inside of circuits. So to start with, I have to introduce a couple of what we call circuit elements. The first is something that you're very familiar with, and it's called a battery. When we put a battery on a circuit diagram, that is a diagram that represents what a circuit would look like, we write it as this symbol, where we have a short line and a long line along two lines that are actually going to represent our wires. And the short line, long line symbol is the thing that defines a battery. The battery has two different terminals, which you've probably seen when you've looked at a handheld battery. It has a positive side and a negative side. And the long line with the battery corresponds to the positive side of the battery, and the minus sign corresponds to the lower side. And when you see a battery in a circuit diagram, what you say to yourself is, that battery has only one job. And that job is to keep the long end, the positive end of that battery, at a higher potential than the shorter end of the battery. So when you go to the box that your battery is coming out of, and you read on the side of it that it has 1.5 volts, that 1.55 volts is what we call the EMF, or the electromotive force. A lot of people say that this is a misnomer, but we'll talk about that later in the semester. The electromotive force is a potential difference across which the battery goes from negative to positive. So a 1.5 volt battery has a difference in potential across the terminals of 1.5 volts. And that is the only job of the battery, is to keep that positive end 1.5 volts on above the potential at the shorter end. And the only time a battery doesn't do that is when we make a mistake and we make it so the battery can't do that. Okay, now our second circuit element, because a circuit with a battery and nothing else would be kind of boring, is something called a capacitor. Now a capacitor symbol is going to look again very much like a battery. It's got two wires, and it's connected to two straight lines, although in this case the two straight lines are exactly the same length. And what those two straight lines are supposed to represent are two, say, plates, or two different conducting surfaces that are separated by some distance, and in between, and you could draw a line in between these two things, there's supposed to be nothing. And so I have two metal plates, or two conductive plates, and those two plates are separated by a space. And that space, of course, makes it so that charge cannot flow between those two lines. Of course, that might seem boring, but it's enough to come up with our first circuit, right? And so I take my battery, which has a particular EMF, and I'm going to label the positive and negative signs of the battery and connect it with some, allow it to have some potential difference across it. And then I'm going to hook that up to a capacitor. And what's going to happen here is that the wire is going to preserve the same potential, right? So we learn that conductors are very bad at creating potential differences because charge is free to flow along conductors. And so this entire right wire here is going to be at the same potential. The entire left wire is going to be at the same potential. And so what we find out is on the other side of the circuit, we end up with a circuit element that has the same potential difference as my original battery. And so I've set up a circuit because it's closed, but what this circuit has actually done was create some sort of static potential difference across the capacitor, which of course, because of electrostatic forces, has allowed charge to accumulate. And what's really interesting about this process is that the charge that's accumulating is going to be the next thing that we study. When I hook a battery up to a capacitor, am I able to calculate how much charge is actually accumulating on that battery? Now, when I try to study this circuit, what I actually see is the battery could be any battery at all. It could be a 1.5 volt battery, it could be a 9 volt battery, it could be a 100 volt battery. surely the same amount of charge isn't going to collect on this capacitor if I hook up a 1-volt battery versus a 100-volt battery. In fact, that's the whole interesting thing about capacitors, is that how much charge accumulates is directly related to what the properties of that capacitor are. In fact, I can boil that all down to the statement that the amount of charge that is actually built up on the capacitor turns out to be proportional to the potential difference that I've applied across that capacitor. And that constant of proportionality is really the interesting thing about the capacitor itself. If I build a capacitor in one way, it's going to be able to accumulate a certain amount of charge per volt. If I build a capacitor a different way, it's going to then provide a different a number of coulombs per volt. Luckily, I can use what I know about potential to actually calculate what this constant of proportionality, which we call the capacitance, actually is. So let's consider the simplest possible capacitor. I just have two parallel plates that are separated by some distance d. And I've chosen parallel plates because I have one plate that has an accumulation of, say, positive charge on the bottom, which means that I have a plate that has an accumulation of negative charge on the top. And I've spent a lot of time studying what the electric field is due to an infinite plate of charge, which is an okay approximation for me to make in this case because I'm talking about plates that are much, much wider than they are separated. And so the electric field inside this capacitor is the sum of the electric field due to the bottom plate, which is just sigma over 2 epsilon naught, plus the electric field to the top plate, which is going to have the same magnitude, and so I end up with an electric field that has a strength of sigma over epsilon naught. Now, if I want to find the potential difference due to that electric field, I find out that the potential difference is, of course, minus the integral of E dot ds, and so the magnitude of that integral ends up being sigma over epsilon naught times d. And so I know that the potential, and there should be a minus sign here, right, because the potential difference across the plates as I've drawn them has gone down by sigma over epsilon naught times d. Okay. But that's the potential difference. So if I want to take that expression that the potential difference is equal to sigma over epsilon naught times d, and I want to change that into the physical parameters of my plate, namely I'm talking about the area of the plate and the distance between them, then I can rewrite sigma as the charge on each plate times its area, and then I can solve for Q, and I get what I had guessed in the beginning was that the amount of charge that's built up on the plate is indeed proportional to the change in potential across those plates, and that constant of proportionality is the exact thing that we call the capacitance. So for the example that I've shown here, two plates, each of area A, that are effectively two-dimensional and effectively infinite, I get that the constant of proportionality, the capacitance, is epsilon naught A over D, where A is the area and D is the distance between them. And what that means is that for every volt that I apply in potential difference across those plates, this is how much charge actually accumulates on them. Now, I could redo this calculation for all sorts of really interesting scenarios. I could think about capacitors that are built out of, say, cylindrical. I could have cylinders that are concentric, right? And when I have something like that, then I can talk about charge building up, positive charge building up on the outside cylinder, and I can talk about negative charge building up on the inside cylinder, and I can solve that problem and find out what the capacitance of that kind of capacitor is. And these are all exercises that I'm going to leave. These are all exercises that I'm going to leave to the problem set. But of course, the simple calculation that I've done here by taking a capacitor, assuming that there's nothing in between the plates, and then calculating the potential difference, and so I'm able to get how much charge is there built up per volt applied, that all is under this assumption that there's actually nothing in between the capacitor. Now, if you went to your favorite fabricating shop and asked them to build you a capacitor with absolutely nothing in between them, they'd laugh at you because that's really hard to do, especially if you wanted to put it inside, say, a television set. So in practice, what we actually do is we have to put a material in between the two plates, almost always a material that's not conductive. But in the case when I do that, I end up with both the electric field that I started with, but a bunch of molecules inside that turn out to be polarized, because every molecule is built of a part that can be moved. There's a positive part of the charge distribution and a negative part of the charge distribution. And so those charges now line up with the electric field, and they cause what we call a secondary electric field to be created inside the non-conducting material, or the dielectric material that's inside the capacitor. And so the total electric field inside a capacitor is actually the sum of the first electric field, that's the one that's actually created by the charges building up on the plates, plus this secondary electric field that's caused by the polarization of the molecules inside the capacitor. And if it were just that, I'd have to stop here, because I'm not really sure how any particular material actually responds to an external magnetic field. But in many cases, I can talk about what are called linear materials, where I'm going to say that the secondary electric field is equal to minus some small constant, which we call epsilon, times the primary electric field. So the minus sign tells me that it's pointed in the opposite direction. The small constant epsilon tells me that it's not as big as the original electric field, but it's proportional to that original electric field. Then I can write down E as the total E as the original electric field, E1 times 1 minus epsilon. And this is only true if I can treat the material as a linear dielectric, but that turns out to be a pretty good approximation for a lot of actual capacitors that we end up building. And so the real capacitance of a physical capacitor has to be modified by this factor of 1 plus epsilon, 1 minus epsilon, which we sometimes call 1 over kappa sub E, which has a very fancy name, which is called the dielectric constant. And so the real capacitance, which I'm going to call C prime, of a capacitor with a material inside of it, is actually the capacitance that I would calculate in vacuum times the dielectric constant. And it's just important to remember this, because the difference between a capacitor that I can think up and do a problem on and one that I can actually build is the fact that the dielectric inside this capacitor generally makes a difference in what I actually measure when I measure the capacitance. Okay, so what are your take-home messages? I can use capacitors to build circuits, and when I put capacitors inside of circuits, charge does not flow across a capacitor. A capacitor, by definition, are two plates that can't touch each other. They can influence each other through the electric field, but they can't touch each other, and therefore charge can't physically flow across it. If I want to find out how much charge builds up as a function of the potential difference I've applied across the capacitor, I use the capacitance, which is symboled by C, which is a measure of how much charge gets built up as a function of the potential difference. And I can calculate C often from first principles, or I can calculate it from the geometry of the capacitor that I'm looking at. And of course, dielectrics modify the electric field inside a capacitor, and therefore they modify the ability for that capacitor to actually store charges.